Assalamualaikum warahmatullahi wabarakatuh. My name is Isma Hasibah binti Zakari. I will present about electricity and magnetism. In this presentation, I will summarize the important knowledge that I gained from Chapter 1, Chapter 2, and Chapter 3. Chapter 1 introduces electromagnetism. Positive and negative charge produce electric fields. When charge move, they generate magnetic fields. A changing electric field and magnetic field together produce electromagnetic wave such as light. Another important concept is electric flux, which help us visualize electric fields. Magnetic fields can be produced by permanent magnet or electric currents. The chapter also introduced the electromagnetic spectrum, where visible light is only a small part. For Chapter 2, starting with the fundamentals of math for electromagnetics, vectors, scalar, and fields. Remember, vectors have both a magnitude and a specific direction, like velocity or an electric field. Scalars, on the other hand, only have magnitude. Think of temperature or electric potential. Finally, fields are functions that assign a vector or a scalar to every single point in space, allowing us to describe physical force at any location. Moving on, let's look at how we present vectors in 3D space using components. We break a standard vector A down along the three primary axes x, y, and z. Here, ax, ay, and az are unit vectors with a length of exactly one that point our way. By calculating the square root of the sum of the square components, we find the overall magnitude. This component breakdown is essential for analyzing physical force acting in three dimensions. Now, let's review basic vector operations. First, the dot product measures how much two vectors line up, giving us a single scalar value. Next, the cross product multiplies the perpendicular parts of two vectors, giving us a brand new vector pointing in a completely perpendicular direction. We also use a vector addition, aligning path end to end to find a direct route, which follows regular algebraic rules like the commutative and distributive laws. To solve real-world problems efficiently, we use three main coordinate systems. Cartesian coordinates use standards x, y, z axis and are perfect for box-like geometries. Cylindrical coordinates use rho, phi, z and excel at analyzing circular objects like wires or pipes. Lastly, spherical coordinates use r, theta, phi, which is the ideal choice for point charge, spheres, or radially symmetric systems like atoms. Often, we need to switch between these systems depending on the problem structure. This slide outlines the exact mathematical transformations. For example, we can shift from Cartesian to cylindrical using simple trigonometry or go all the way from cylindrical to spherical coordinates. Converting our coordinates properly can turn a highly complex physics problem into a much simpler calculation. Next, let's look at vector calculus foundations. When integrating along lines, surface, or volumes, we must define differential lengths dl, differential normal areas ds, and differential volumes dv. As you can see, these definitions change completely depending on whether we are working in Cartesian, cylindrical, or spherical formats. Setting this up correctly is the secret to solving complex electromagnetic integrations. Now, we enter operation territory with the gradient denoted as del V. The gradient operations apply to a scalar field like temperature and turn it into a vector that points directly toward the steepest rate of increase. This slide shows the exact partial derivative formulas used to find the gradient across all three coordinate systems. Next is divergence, written as del dot A. Unlike the gradient, divergence takes a vector field and turns it into a scalar. It measures how much a field is spreading out or converging at a specific point. Think of it as mapping out the sources or sinks in a fluid flow or an electric field. The formulas vary significantly across Cartesian, cylindrical, and spherical boundaries. Our third major vector operation is curl, written as del cross A. Curl measures the rotational property or how much a vector field swirls around a given point. This is incredibly important when we study the rotation of fluid flows, or the behavior of magnetic fields. Because calculating curl involves cross-product expansion, the metric derivative look a bit unique for each coordinate system. Finally, we have the Laplacian represented as del square. The Laplacian measures how much a point's value differs from the average value of its immediate surroundings. It's essential a second-order derivative operation that shows up everywhere in heat transfer, wave propagation, and electric potential equations. Mastering these coordinate representations completes our core vector toolbox. To conclude chapter 2, let's look at two fundamental theorems that tie everything together. First, the divergence theorem allows us to convert a closed surface integral into a volume integral, which is incredibly useful for analyzing enclosed charge distributions. Second, Stokes' theorem relates the curl of a vector field over an open surface to the line integral around its boundary curve. Both of these powerful tools bridge the gap between microscopic and macroscopic calculus, forming the absolute backbone of electromagnetism. Now we are looking at chapter 3, starting with Coulomb's law. This law explains the electric force between two-point charge Q1 and Q2. The force always acts along the line joining the two charge. It is directly proportional to the product of the charge and inversely proportional to the square of the distance between them. We use a constant K which depends on the permittivity of free space. Next, let's discuss the electric field, denoted as E. It is measured in newtons per coulomb or volts per meter, representing force divided by charge. We can find the electric field for a single point charge or a system of multiple charge. For spread out charge, we calculate line, surface, or volume distributions. We also use quick specific formulas for special case like an infinite line charge or an infinite sheet charge. Moving on to electric flux density, which we write as D. It is defined simply as D equal epsilon naught E. The total electric flux is the integral of D over a surface area. On the right side of the slide, you can see how we adapt the formula to find the flux density for different shapes, including a single point charge, a line charge, an infinite sheet, or a volume charge. Now, let's look at Gauss' law. This important law states that the total electric flux passing through any closed surface equal the total charge enclosed inside it. If we express the enclosed charge as a volume integral and apply the divergence theorem, we get a very clean final result. The divergence of D equals the volume charge density, rho V. Finally, let's look at the relationship between the electric field and potential. Because the electric field is conservative, the line integral around a closed path is always zero. By applying Stokes' theorem, we get Maxwell's second equation, which states that the curl of E equals zero. This leads to our final gradient formula, showing that the electric field is the negative gradient of potential, E equal to negative del V. That's all from me. Thank you.